Hi, I'm Robert Crow, and I'm here today to talk about ML engineering for production ML deployments. Let's get started. We're going to start with a little thought experiment. I want you to imagine that you're a retailer, an online retailer, and you're selling shoes, and you're using a model to predict your click-through rates. And that's helping you decide how much inventory to order. So that sounds good. But suddenly, the AUC on your model, not on everything, but on a particular slice of your data or a particular part of your inventory, men's dress shoes, that just goes through the floor and you have a big problem. But why? I mean, you trained your model, you tested it with your test data, your holdout set, everything looked good. Why do you have a problem now? And maybe more importantly, how do you even know that you have a problem? Well, unfortunately, there's a pretty good chance you'll find out when you either order way too many shoes or not enough shoes. Remember, we're using this model to predict how much inventory we should order. So when it goes bad, our inventory ordering goes bad. The moral of the story here is that the world does not stand still, and your model needs to adapt to change. This is a big difference between production ML and what you might have done in a research or an academic setting. So production ML and change are very closely tied. There are easy problems, and we've all seen these. These are things that change very slowly, and there's very good data sets that are out there that are well labeled. Things like recognizing cats and dogs, they don't change very much. But some things do change, sometimes on the order of weeks, things like fashion. So in this case, we're selling shoes, and styles of shoes change, certainly with different seasons, but also just, from for progression of time. So that means that the model performance that you have that's working with shoes is also going to change and decline over time. Really hard problems are where the ground truth changes very fast, on the order of days or hours or minutes. And in this case, you're almost always going to be retraining your model because of declining model performance. You may also be coming up with model improvements, and that's great. So when we get into machine learning, we often focus on our modeling code. That's, after all, it's the secret sauce that we're all excited about. It's what research papers are written about. It's where a lot of the advancement is happening these days. It's great stuff. But when you get into a production setting, you discover that, well, we've measured it as maybe 5% of the code to put an application or a service into production. So all these other pieces are critical for the success of whatever you're trying to do. And people, unfortunately, have learned this the hard way. This is kind of a famous tweet now where Gina Blabber from O'Reilly had a model that they trained in 3 weeks, and then 11 months later, they still are unable to deploy it. So this gets us to some of the issues in production machine learning. You have all of the issues that you have with normal machine learning development. Assuming you're doing supervised learning, you have to label your data somehow. You do have to worry about whether or not your training data covers the same feature space as the prediction request that you get. And you want to do things like minimize the dimensionality and maximize the predictive information in the data. You also need to consider things like fairness, which can have a big impact in a lot of areas, and including your brand. And in many domains, there's rare conditions that you have to be particularly careful about. This is a big problem in both healthcare and fintech. And you also discover that data has a life cycle, and you need to manage that life cycle. That's closely tied to the change we've been talking about. But along with that, you're going to take a piece of software and put it into production. So you have all the same challenges that you have with any production software deployment. You've got to worry about, how am I going to scale this? How am I going to extend it? Can I control the configuration in a well-defined way? Is it modular? Is it testable? Can I monitor it well? And security as well, because as we know, there's attacks that happen against machine learning models. You also have to worry about costs. So it's this balance that you have to strike, trying to reduce your costs through reducing the compute resources that you use, both for training and for inference, and the cost of data collection and the labeling that is required. That can be very expensive in many domains, and even simple things like storage. And how you're going to set up the systems to supply that data when it's time to generate a prediction for inference. And you need to balance that against your goals, because as you simplify your model, it has an impact on your accuracy. You also have to think about interpretability. So is the model that you have interpretable, or do I have to use other tools to try to pull interpretation out of it? The latency of your model, the more complex it is, the slower it's going to be and the more compute resources it's going to require. And in mobile and IoT and edge scenarios, there's even more challenges because you have limited resources on those devices and you're often working in a disconnected scenario. So Google has been doing production ML for quite some time now. And we've done a lot of research into it and written a lot of great papers. So this is a fairly good selection. Certainly, if you read through all these, you'd know a lot about what we're doing and what the state of the art is in the industry. One of the key terms that's coming out these days is ML-Ops. So these are a couple of different definitions. People have different ideas about what ML-Ops is. Some people are more focused on this collaboration and communication between data scientists and operations professionals, and that's certainly very important. Other people tend to focus on the automation aspects of ML-Ops, and that's also very important, especially to quality and in some cases to regulatory requirements as well. And other people, many people have put out different architectures. This is one from the CD Foundation, but they all, are roughly the same. You're talking about an ML pipeline that you're going to use to train your model in a very repeatable way and well-controlled process. Okay, so now we've got all these challenges. What do we do? Well, Google's answer has been TensorFlow Extended, or TFX. Google uses TFX all over Alphabet for the majority of the ML applications that we put into production. And now we make it available as an open source platform for you to use as well. So you probably recognize some of the icons here. It's all over the Google and Alphabet applications. And our partners as well. So many of our partners, since we open sourced it, have adopted TFX as their platform as well. And an interesting case here is Twitter, because Twitter had a significant investment in Torch. And they took a look a couple of years ago at where they should, make their investment moving forward. And they chose TensorFlow and TFX, moving away from things like PyTorch because of what was offered by not just TFX, but the whole TensorFlow ecosystem. So at a high level, this is kind of what TFX looks like. On the top in gray, you see the different tasks that you're going through to train and deploy your model. In the middle, you see libraries, and those libraries are also open sourced, and they're available by themselves. So you can use them by themselves, or you can also use them with the components of a TFX pipeline, which are in orange at the bottom. And we'll go through these in a minute. So this is kind of the hello world of TFX. It's the starter pipeline that you begin with when you first install TFX with pip install. These are what we call the standard components. And on the right there, you see the deployment targets that you can deploy to from a TFX pipeline. So TensorFlow serving, if you're deploying to a server cluster, TensorFlow Lite, if you're doing a mobile or edge or IoT application, TensorFlow JS, if you're deploying into a web browser or a Node.js application, or TensorFlow Hub or something like it, if you're going to take that model and reuse it later for transfer learning or for generating embeddings or something like that, maybe in an ensemble. So the things that we've been looking at are components. Let's dive into what a component is. A component has three main parts: a driver, an executor, and a publisher. The driver and publisher in gray here are largely boilerplate code. You can change them. Chances are you probably won't. Most of what you're going to work with is in the executor. That's where you're going to create your custom components. And we'll go into some detail about different ways to do that. A component by itself receives its input from metadata, except for the very first component in the pipeline, which is receiving it from some data source. It does what it's going to do, and then it pushes its result into metadata. So that's how components communicate with each other. The input into a component is through a channel, which is an abstraction that makes it easy to pull that artifact out. And the same thing on the output side. You're putting your artifact into metadata over an output channel. So TFX components communicate with each other, and data flows through a pipeline through metadata. So an output artifact from a upstream component is put into metadata, and then components that depend on that will pull it out of metadata, do whatever they're going to do, and put their result back into metadata for other components downstream that are going to depend on it. So we're running a number of tasks here. We need some orchestration to do that. And TFX is open at the orchestration layer. Out of the box, we support actually several different orchestrators. Apache Airflow is a popular one, Kubeflow as well, and some others that we'll talk about in a second. But if you have a different orchestrator that you want to use, you can plug it into TFX and work with that. We also offer orchestration in a notebook. So notebooks are great tools for doing experimentation or development. And by running an entire pipeline in a notebook in just, you can run it on your laptop. It's a very easy and friendly way to work with and understand your pipeline while you're developing it and your components. At the end of the day, you're going to end up with the same directed acyclic graph, or DAG. And depending on which orchestrator you're using, it will be displayed differently, but it's the same DAG. So we've mentioned a couple of times that there's a metadata store. Let's dive into that. So first of all, what's in it? Well, there's artifacts, and artifacts have properties and types. So for example, a trained model is an artifact. A data set is an artifact. A transformed data set is an artifact. A schema is an artifact. You get the idea. Pretty much everything that you work with in a pipeline is an artifact. And artifacts are grouped or associated with each other by their execution run. So an execution run is a pass through a pipeline. It's a complete run through a pipeline. And if you want to understand how that run worked, it's very useful to be able to trace back using the artifacts that were part of that run. So that gives you the ability to understand the provenance of your artifacts across executions. So if you want to trace back, that's a great tool to be able to do that. So a key capability here is that you can just check to see what data a model was trained on. which is often very important, especially for interpretability and regulatory requirements. Another nice functionality is to be able to compare previous model runs. You could be looking at the difference between what you did today and what you did 6 months ago, and trying to understand how your model changed and how your results changed. And we're looking here at TensorBoard that's allowing us to compare two different runs. You also don't want to rerun a component if you don't have to. Remember, TFX is designed to handle very large data sets and large compute resource needs. So it could take quite a while to run a component. And if you don't have to, if the input to a component hasn't changed and the component configuration and so forth hasn't changed, then you just can pull the previously generated output from cache and reuse it. And that works with warm starting as well. So if you're training a model and you've trained for 10,000 epochs and you decide you want to train for another 5,000, you can start over from where you left off with warm starting. So since we are dealing with large amounts of processing and data, a distributed processing framework really makes that possible. And what TFX uses is Apache Beam. So if you're not familiar with Apache Beam, it's a unified batch and stream distributed processing API on top of other frameworks. So Apache Beam is an abstraction layer on top of things like Apache Spark and Apache Flink and Google Cloud Dataflow. It also has a really nice direct runner, which allows you to run without configuring a cluster or anything. You can just run, I run it on my laptop all the time. So it's a very nice thing for doing development. And Beam supports a number of different platforms that you can run on, and potentially in a single company, you could have more than one of these, different teams or different geos, what have you. It also supports a number of different SDKs in different languages. So working with one of those SDKs and putting Beam in the middle of that, you create a Beam pipeline or a Beam request using the Beam API. That then gets translated into the target of whatever you're actually working on, and then a result is generated. Or looking at it a little differently, I have a component here that's running, and the executor in that component, we could be running this on either in a Docker container or a full OS. The executor is going to use Beam, and it's going to issue a request, a Beam pipeline, which then gets sent off to this distributed cluster that I've set up, and a result is generated and then translated back into the Beam paradigm or SDK for a Beam result. So that's how components can leverage large amounts of compute resources in a cluster. The TFX standard components, many of them do use Beam to do their processing. And again, this is like the Hello World TFX pipeline. This is just where you start. You can add your own custom components to it. So starting at the beginning, we have example gen, which is going to ingest our data. And there's a list of different example gens that are available. We're just looking at a couple here. The main thing to understand is that it's going to ingest your data and split your data, and it's going to use Beam to do that. Then we work with statistics gen to try to understand our data. We're really following a fairly basic ML development process here. And the first thing to do is understand our data. So statistics gen helps us do that. And it provides some visualizations that help us really dive in and work with our data and understand the characteristics of it. Then we have schema gen. And schema gen is going to try to infer a schema, the types of each of your features. That includes determining what the valid values are for categorical variables. So you may know more than SchemaGen does. And if you do, then you want to curate the schema that SchemaGen gives you, but at least you have a good start. And in many cases, SchemaGen gets it right. Then we have example validator. And example validator looks for problems. So it's going to look for things like missing values or values that are the wrong type, maybe a float instead of an int. It's going to look for categorical variables that either it shouldn't see or that occur so rarely that it thinks that possibly they could be a problem. And it generates a report for you to review. Then we have transform. Transform is where feature engineering does. And since feature engineering by itself can be sort of arbitrarily complex, the code, as you can see for transform, is a little more complex than it is for other components. So it just depends on what you need to do for your particular model and data. Maybe all you need is something like a z-score, like we show here, or you could be doing, generating embeddings and vocabularies and what have you, a lot more advanced kinds of things. It just depends on what you need. At the end of the day, transform is going to take whatever feature engineering you've done and translate that into a TensorFlow graph. That graph then gets included when you train your model. It's the input to your model that's going to do the transformations you need for your feature engineering. And it also gets deployed when you deploy your model to any serving environment. So wherever you deploy your trained model, you have the same feature engineering that is going to happen in that model. That eliminates the problem of training and serving skew. Trainer is next, and trainer is going to train your model. So it's taking the input from transform, including that graph we talked about, and it's going to take your model code and train it and probably produce a saved model, which then gets used by TensorFlow model analysis and TensorFlow serving. So the code for trainer is about what you'd expect. It's things like the number of steps and where to get the input and so forth. You can also train not only a TensorFlow model with either Keras or the Estimator API, but a scikit-learn model. And by integrating it with Cloud AI Platform, you can also train an XGBoost model or a PyTorch model. There are some advantages, of course, to using TensorFlow. One of the tools that you have when you train a model is TensorBoard. And so that's part of what is integrated into TFX. And one of the nice things, because you have the metadata, is that you can compare different runs of TensorBoard and understand the difference between the training that you did just now and what you did at some point in the past. We also have hyperparameter tuning. So this is the tuner component, and it's using the Keras tuner API to tune your hyperparameters automatically as part of your pipeline run. Next, we have evaluator. And evaluator does a couple of different things. First of all, it evaluates the performance of your model, but it does it not just at a top level across your entire data set, but also on particular slices of data that are important. So if we go back to our first example, we would want to evaluate the performance of our model on men's dress shoes and understand how does it perform on that particular part of our inventory? Because as we've seen, having problems in particular slices of your data can be a real problem for your business or organization. The other thing that evaluator does is a comparison between what you already have in production and what you're training now. Because as you probably know, just because you trained a new model doesn't mean it actually performs better than what you already have. And we give you some visualization tools to help you really dive into the performance of your model, including at the slice level, and really understand how it's performing. Then we have infravalidator. And infravalidator does a very simple but important task. It makes sure that when you deploy your model, you can actually run it. So can you run it on the hardware that you have when you're going to be running inference? Will it deploy? Will it load? And you can try running a few examples against it just to make sure as well. If both infravalidator and evaluator decide that your model is good, it's called blessing the model, then pusher will push it to your production deployment targets. So could be more than one target, could be just one. It just depends on how you have your system set up and where you want to deploy to. We also have bulk infer. So you might have noticed that so far the TFX pipeline that we're running is just doing training. It's not doing inference. Well, bulk infer is where you can do inference in a TFX pipeline. And it's great for doing batch inference across a lot of examples. And one of the nice things that it does is it distributes that inference across one of those distributed processing clusters that we talked about earlier. So it's a great way to leverage the resources that you have. In addition to components, there are also pipeline nodes. Pipeline nodes are not components. They are special purpose classes, and they're used specifically for interacting with metadata. So for example, if you have an external artifact that you want to import into your metadata store, you can use a pipeline node to do that. Or if you want to retrieve some artifact that you have in metadata, you can use a pipeline node to do that. So the first case is the importer node, where you're pulling data from outside the pipeline into your metadata store, and you're going to use it somehow probably. Then we have resolver node, and resolver node is used to query your metadata in a couple of different ways. So you need to identify, the query that you want to do, and there's a couple of different types of resolver nodes that you can use. So the first one is the latest artifacts resolver that is just looking for the most current artifacts from a given channel. So that's going to be coming from a given component. So for example, if you wanted to query the latest schemas from SchemaGen, you could use latest artifacts resolver to do that. The next is latest blessed model resolver. And actually the evaluator component that we looked at earlier uses this. It's going to return the latest blessed model, meaning the model that you currently have in production. And that's going to be used by evaluator, for example, to compare with what you just trained. From TFX, you can also train models for mobile and IoT applications using TF Lite. So TF Lite is supported, and it's a really fairly small change to your pipeline to support TF Lite. You need to invoke the TF Lite rewriter, and you need to evaluate, of course, your TF Lite model. So this is what the code looks like. So this is invoking the TF rewriter. This is actually the signature portion of that, so that you have this tensor spec that you have to define as part of your signature. And then you invoke the rewriter. So you have a rewriter factory, and you're using the TF Lite rewriter here. And it's going to rewrite rather a saved model. You also need to evaluate your TF Lite model. So this is how you plug that into the evaluator component. As you can see, it's a very simple, it's a very small amount of code. But one of the key aspects is that you can create your own custom components. The components that come out of the box are just where you start. So there are three ways for you to create custom components. A Python function, which is the easiest way to do it, and you just add a decorator and some annotations. We'll look at that in a second. Or if you have some more complex processing that you want to do, possibly in a different language, you could use a container and wrap that container as a component. And you can also just extend the component classes of an existing component. So if you have something that's close, or if one of the standards components standard components is close, you can just extend that and use that as a custom component. At the end of the day, you're going to plug your custom component into the pipeline just exactly like any other component. There is no difference between that and a standard component. So for a Python function-based component, you're going to decorate it with the add component decorator at the top, and then you're going to add annotations to the arguments. It's really very simple, and it's a great way to get started with custom components. A container-based component, if you're working in containers, this is also very simple. So you need to tell it, of course, where to find your container, but then you just add some annotations to the arguments and you wrap it in a function call, and you've got a component. Or you can just take an existing component and create a custom executor for it by extending the executor class of that component. And this is just basic Python, extending a class. So TFX works in a number of different environments. It works on my laptop. It works on a server or on-prem environments, different clouds, including the Google Cloud as part of Cloud AI Platform pipelines. So at a very high level, this is what it looks like. You have TensorFlow that is running in TFX. That in turn is running on top of Kubeflow pipelines, which is running on top of the Google Kubernetes engine or GKE. And then you have all of the Google Cloud services that you can leverage from there. At a little deeper level, this is what it looks like. So again, we have the TFX SDK that's running on the KFP SDK that is in turn running on GKE and using the cloud services. You also have Jupyter Lab, which is part of the Cloud AI pipelines, platform pipelines. So Jupyter Lab is a great environment to develop your pipeline and do experimentation and so forth. But at the end of the day, you end up with the same TFX pipeline, regardless of where you put it, whether you're running it on your laptop or on a Kubernetes cluster in the Google Cloud. It's the same pipeline. And that's TFX. There are standard components for scalable mission-critical needs. You can add, and probably will, add your own custom components. We give you powerful metadata and distributed processing, along with flexible orchestration and support for several different frameworks. Here's our website. If you haven't seen it, go take a look, tensorflow.org/TFX. And here's some resources to help you get started. So there's that website, our repo on GitHub. We have a community. I hope you'll join. And of course, there's some YouTube videos out there. All right. Thanks very much.